Perfect. Okay, so good morning, everybody. Morning, afternoon, night, as we are connected from quite a few places. So thanks a lot for joining us for this second webinar on radiation facilities organized by RADNEXT. So I will just quickly share an intro slide to introduce a bit the topic of the day. So essentially, as I think many of you know, RADNEXT is an EU-funded project putting together a network of facilities plus research institutes and industry around it, and it's essentially aimed at enhancing the accessibility to facilities for users and the quality also of the service and the beam time that is provided. So we are providing free of cost beam time in a broad variety of beams, heavy ions, protons, neutrons. This is for worldwide users, so anybody is welcome to submit proposals. We just closed our fourth call for beam time a few days ago, which was actually a very successful one. So we will be busy now reviewing and assigning the related beam time. The next opportunity will open in June. So those of you interested in submitting experiment proposals, please keep an eye on that. And of course, more information is available on the project website as well as on the LinkedIn site, which is quite active with updates and news about the project. So more specifically of what we are here gathered today. So we are organizing a series of webinars on present and future radiation facilities worldwide. This is aimed at, let's say, less conventional or less consolidated facilities or approaches. Today we have the pleasure of having Marco Petasecca with us, Professor Marco Petasecca from the University of Wollongong, and with vast experience on radiation damage, especially related to sensor damage, for instance, in the collaborations with CERN and the CERN experiments, as well as also a lot of experience on radiation facilities now in Australia, but also previously in Catania in Italy, for instance. So setting up facilities and making them compliant with the standards and with the requirements of the different agencies and institutes. So I think that's at the very heart of the RADNEXT project. So it's really an excellent topic to cover. Of course, this is the second of the series. The first one is available as a recording for those of you that are curious. The first talk was on SE testing at NSRL. We will announce the next webinar at the end of today's presentation. And as mentioned, we will be recording also so that we can then, if we want to come back to some of the points, that we have the opportunity to do so. But then the discussion at the end of the presentation will not be recorded. So there we can, of course, be proactive in asking questions and any curiosity that we may have related to what Marco will present to us. So with this, I stop my sharing, and thanks a lot, Marco, for being with us. The floor is yours, and we are very curious to see what you have to tell related to the future of the Australian facility network. So thank you very much.
Excellent, Ruben. Thank you very much for the opportunity to actually present to all of you guys the effort we're trying to put together to organize this workshop and the network. So let me share with you my screen if I can, which obviously is not this one. And I need to find the presentation on screen too, which probably is this one. Yes. Can you see my screen now, or is it
still?
Yeah,
perfect. We don't see it in full screen. We see it kind of in presenter mode, but I guess you can enable that.
See if I can. Can you see now?
Yeah, that's perfect.
This is okay in full mode. Excellent. Okay. So the topic, as Ruben mentioned, I mean, first of all, thanks Ruben for inviting me on this great initiative RADNEXT is organizing, because I think it's important to have this kind of knowledge worldwide on the facility available and what actually is up there for, I mean, especially for the space industry, which is growing so fast in couple of years. So the National Space Qualification Network, or NSQN in short, is the Australian effort to create essentially a network of facilities able to provide a service of, I'm not saying a qualification, but actually more testing and defining the limit of use of devices. Qualification is often a word which is not probably used in industry, and may actually be kind of dangerous in terms of liability, but this is a discussion which is much wider than the purpose of this webinar. So first of all, because I'm coming from Australia, we acknowledge our what we call our country, and that essentially is what I would like to do is acknowledge and pay respect to the traditional owners of the land where I study, where I live, and where I thrive. That particularly is the Darawal people, which is the tribe which was essentially here since probably 15,000 years ago, and we thrive on their land, and we use to pay respect to the knowledge of their elders and to the custodian of the country. So the outline of the webinar essentially is an introduction of the vision of the network that the Australian Space Agency is essentially funded for what concern irradiation facility for single event effects and for total ionizing dose. Then I will show you essentially mainly the two facilities which are available to do ion irradiations, displacement damage, single event effect, and total ionizing dose. But then we have also we are also creating a laser scanning facility for single event effect, particularly. We're trying to create a research stream on the use of synchrotron microbeam light in order to create single event effects and a single event effect mapping. And as I said, we have a simulation facility as well, an environmental testing facility, which are part of the network as well. So in the vision of the network essentially is to gather together in one single body, essentially 6 main partners, each of them with their own expertise. The main one is ANSTO, which is the Australian Nuclear Science and Technology Organization, and the Australian National University, which is in Canberra. ANSTO is in Sydney. I'll show you a little bit the geography of this partnership. So essentially the Australian Space Agency, what he recognizes is how critical it is to have sovereign capabilities in terms of radiation characterization and testing, particularly now that the space sector, the space industry is growing so fast in Australia. We have an increase of 30% almost every month in terms of investment in the space industry. And that is something which is supposed to grow for the next 10 years at this kind of level. So the National Space Qualification Network, what it was to create is a hub which allow industry to access these services and be able also to educate the industry in terms of what are the requirements for electronics, particularly, but also equipment and mechanics to be essentially to survive a launch and a mission in space. So to give you an idea of the facilities are essentially across ANSTO, which is the Nuclear Science and Technology Organization, and we have the where we have the gamma irradiation facility, which we call GATRI. We have the X-ray synchrotron radiation facility, which is a synchrotron with 8 different beam lines. And then we have the Center for Accelerator Science, which is the facility which provides the ion beams and the acceleration, and the two different type of accelerators. University of Wollongong provides, which is where I come from, is the laser facility where we are going to test and mapping single event effect. And then there is the Australian National University in Canberra, which is the one which provides a higher energy accelerator facility, and the environmental facility where we are going to test essentially some of the satellites and the mechanical strength of those. So to give you a little bit of perspective on the geometry, the geography of our group, ANSTO is placed in Sydney, the laser facility in Wollongong, which is a few 80 kilometers south of Sydney. The heavy ion accelerator facility in ANU is in Canberra, which is in the Australian Capital Territory. And then we have the synchrotron, which is placed in Melbourne on the south, in South Victoria. So this is essentially the main facility. Then we have, if you remember, we have 3 different industrial partners, which are located respectively in Brisbane, in Adelaide, and in Perth. And they are essentially the ones which are providing most of the consultancies for what concern the end user of this consortium, of this network. So in starting from the first organization, this is the ANSTO, which is a part of the National Research Infrastructure for Australia, and is funded directly from the government. ANSTO provides access to 3 different facilities, and I'll show you essentially which one, the characteristics of each of them individually. So, for example, the first one, which we call the CAS, or the Center for Accelerated Science, provides essentially the accelerator of ions using 2 different types of accelerators. One is called Antares, which is a Van der Graaf 10 megavoltage, which provide the high energy ions. And then we have a Sirius, which is a Pelletron, is a NEC Pelletron recently installed, which is shown in figure on the right side, and provide a 6 megavoltage accelerator. In both of them, they have a unique facility, which is the heavy ion nuclear microprobe. So they essentially are equipped with a raster scanning system, which is able to excite and move the beam, which is a microscopically focused on the device, and is able to raster scan the device in the vacuum chamber. Some of the reference here is from Zeligov-Ostrovich, which you can use for further detail on some of these devices. So the CAS accelerator, essentially, this is a sort of summary of the energies available and the characteristics that can be used with the heavy ion microprobe. The energies that they go from essentially 17 MeV up to 48 MeV from alphas to alpha, from proton to carbon, and the currents that they can be tuned from essentially nanoamps to microamps, and even reduce further for a single event effect. Particularly for the single event effect, I think it's very important to highlight the IBIC, which is the heavy ion microprobe facility, where submicron ion interposition accuracy is available, and it can be achieved in a grid of over 2 by 2 centimeters square of area. The resolution is essentially in the order of the microbeam, the micrometer, and that gives essentially, it's possible to have a current from the picoamp to the nanoamp focalized on 1 micron spot size. This clearly is extremely important kind of facility, because it helps to essentially combine some of the advantages of the ion scan with the microprobe in terms of detecting a specific area of the chip and create enough energy deposition to trigger the single event effect. Essentially the mechanism in order to achieve that, this is an example of the focusing procedure which is achieved, and then the raster scanning obtained essentially on a device, on a large area device. The resolution obviously is parameterized over a metal grid, for example, where you can verify the actual resolution and accuracy of positioning of the microbeam in respect to the device. And then you see the zoom that it can be achieved using essentially the focusing capacity of the raster scan. So in terms of the range achievable in materials, what we present here is essentially a collection of the combination of different species and different energy ranges, and that shows that we are comfortably able to achieve a few hundred micron of penetration depth to achieve even at the deepest sites in silicon. I think this is very important to show that it's true that the accelerator doesn't have a very large energy in respect, for example, to other facilities like BNL in the US, etc. But with a careful managing of the species and the energy combinations, we can definitely achieve the possibility to deposit energy in a specific depth in silicon, and that is what is at the end is important for single event effect. There are effects that can be also studied with these low energies associated with track structure, effect of the track structure on the single event effect cross section, which is something which is part of the program of CAS, and where we have a very strong experience even in the past. Now there is also another factor which can be highlighted, is the fact that we can use this beam for displacement damage, and that means what we need to achieve is not only resolution but also intensity and flux of the beam, fluence of the beam in terms of current which is available for the accelerator. In CAS, they're doing also various radiobiological studies which require instead a very fine control of the current, and that is essentially to achieve few very low dose rate kind of deposition. In order of very important for single event effect and characterization for space is access the beam in air, for example, especially because sometimes the systems they can be quite extensive in terms of board size and area. So what the team in CAS developed is an ambient chamber, which is right close to the vacuum chamber, which is used for the microprobe. And in that environment, they already come up with some testing where the ion beam is essentially fit through a silicon nitride window, and the sample is able to be accommodated into the ambient chamber and scanned across the surface of the sample, which is in that case 10 by 10 centimeter area. Having such energy in the accelerator clearly require the capability to do the capping of most of the electronic packages which comes up with commercial off-the-shelf parts, and this is what essentially CAS procure using the NSQN funding, which is the capping machine able to remove most of the plastic packages which comes with commercial devices. And this system has been successfully tested, and some of the parts which have already been tested on this device. We don't need to forget that clearly any irradiation facility requires also a careful estimation of the penetration depth and simulation of using, in our case, a JAM4, where we have a very strong expertise in some of the team members of CAS, and also in UOW, where Susanna Guatelli and Stefania Peracchi, they have been essentially trained, and they are part of the JAM4 collaborations. So they actually develop code for JAM4. This is the decapsulation machine, which is using the chemical etching, and there is also a facility associated with it, which is the laser etching, which is able to remove selectively by a laser the layer of plastic above the chip, keeping the functionality of the chip intact. So this is a detail of the chamber that we use, that the CAS team use in ASTO. And this is an example. On the right side, you have an example of the way that the chip is accessible in the ambient chamber, but also in the vacuum chamber using some feed-through, which can be customized specifically for the chip which is under test. This is the kind of capacity which is able only when you have a team of, or an electronic service, we call it in Europe, which is able essentially to work on the specific customer setup. Experience with this, experience associated with the IBIC and the CAS accelerator facility is extensively proved in the literature. You may actually search for some of the characterization has been done in the past on microdosimetries, solid state microdosimeters for UOW, where we developed this kind of technology. And we successfully tested the charge collection efficiency of such kind of devices using the IBIC and the CAS facility. So you can see, for example, here a very simple example of charge collection efficiency distribution, or map, if you like, of protons which are irradiating a 10 by 10 micron area, and they show essentially the efficiency of the collection from the devices. So as you see, the machine is up and running and is available for customer to be used. These are some of the examples of the projects that they are running at the moment in CAS, and particularly there is some of them are related, for example, to perovskites or polymer to be used in space applications. There are projects associated with solar cell, for example, other with polymer development, like the one which is with RMIT, which is the University of Melbourne. And there are other continuous project with CMRP and the University of Wollongong within the project of microdosimetry. And there is recently an SRAM memory, which is used, has been developed in Melbourne by Jafar Shojai, which is essentially has been tested with a device for SRAM, for single event effect and single event upset, actually, and displacement damage as well. So you see there is already an extensive experience in CAS, which make the ideal facility to be part of the network in Australia. So moving on the second facility for ion irradiation, we take a ride to Canberra from Sydney, and we essentially go to the Australian National University, where the heavy ion accelerator facility is built. And this is essentially an overview of the energies available in the facility, with different atomic species available for acceleration, which they go essentially from protons down to gold, with an energy range which goes essentially to few tens of mega electron volt per nucleons. I think it's a 49 mega electron volt. In that sense, what we can achieve is pretty high LET expressed in mega electron volt per milligram per centimeter square, as in space industry they typically do. And you see that the range in silicon is the one which is typically used for microelectronic industry. Clearly, for more complex devices, like for example, FPGA or signal processors, probably what is necessary is still the thinning of the package and the thinning of the substrate for some other packaging, more advanced packaging technology, like for example, ball grid array or flip chip. But in any case, that these are technologies which are commercially available and is the services which are relatively cheap in terms of preparation of the samples. The facility in NU is a sort of developing a kind of project. Remember that the funding of the network in Australia started essentially in June last year. And we are at the moment in NU, they are at the moment in the procurement phase. The design is complete. The procurement phase, which always is suffering of the drawback from COVID and the availability of some of the resources worldwide. So at the moment, what they developing and they are assembling is this is the design of the beamline. I started from the end with essentially a vacuum chamber, a large vacuum chamber, which can accommodate electronic boards up to 60 by 60 centimeters square, and they have a scanning device, a beam defining and characterization device, which is just before the vacuum chamber, where essentially there is a thin scintillators for flux measurements, and there is a device which is able to map the fluence of the beam. The beamline also is equipped with a scanning system where essentially they are using it to scan across a large area, which I'm talking about 4 by 4 centimeters square, and that is essentially to create a uniform, as uniform as possible, distribution of the flux of the beam across the area. And then there is the accelerator, which is again a 29 MeV up to essentially able to accelerate the problems up to uranium. So this is some of the screenshot from the beamline, where the accelerator door, where there are the quadrupoles for the alignment of the beam and the scanning of the beam, the scanning device of the beam, and the visualization of the prospective position of the vacuum chamber, which is this big device sitting on the floor right there. So this is the scanning system for in IFE, and that is the actual scanning range is 7 by 7 centimeters square, but the overall usable uniform distribution of the beam is across a 4 by 4 centimeters square area. Uses essentially the focus system, the focus beam system, and then a refocusing for to create essentially the collimated beam necessary which will be characterized at the end of the beam line. The collimated beam is essentially is a microspot which is scanned across the surface of the sample, and there is a real-time flux monitoring able to give based on plastic scintillator and a silicon photomultiplier readout. And then there is essentially a beam profiler based on a segmented Faraday cap, which is able to measure in online the intensity. There are two different settings possible in the beamline, which is the high intensity and the low intensity based on the flux and the which can span essentially across a 12 order of magnitude in terms of current. So this is a sort of highlight of the scanning beam and the radiation chamber, which has been designed with the capability to move the sample across the beam or move the beam across the sample. Depends on the relative dimensions of the device. Is interesting the way that even if in vacuum, the team in Canberra, they essentially designed a very intelligent, a very clever way to create a fit-throughs of the signals, which are able essentially to maintain a very high bandwidth through the fit-through, able to synchronize then the device in respect to the beam, and eventually to be able to trigger the beam in respect to the clock of the devices. And that is something which can be very useful to study worst case scenario of single event effect triggering conditions. One of the main advantages that we would like to stress over essentially this presentation is the fact that the entire beamline has been designed to do single event effect, and using clearly the available acceleration from the tandem accelerator, but it's been designed with in mind the idea that we can give the maximum versatility to the customer. So the entire NSQN, what it wants to create, as I said, is an hub where the industry can access and use essentially the services in a very friendly kind of way. And that's possible only, in my opinion, and in the opinion of the ANU team, to start from the design of a very versatile and user-friendly data acquisition system, which can be interfaced to the device. Without that, we know that it's going to be extremely painful, the whole data acquisition system from that is done using, for example, LabVIEW in the case of the University of Canberra. But then we have also the possibility to give the user the possibility to change different energies in a quick way, so that they don't lose too much beam time, and that is approximately estimated in approximately 20 minutes. But also to have the possibility to focus the beam on a very specific part of the device, and that is, I think, is a very important kind of service, which probably is not as diffuse as we think. Now, moving on, some of the characterization that they are doing in Canberra, I would like to show you a couple of devices that they have in the space environmental testing facility that we have, and that is essentially the National Space Test Facility. So it's the NSTF, where they hold a thermal vacuum test facility, which is a large, they call it the Wombat XL, which is a large vacuum chamber with the possibility to store a maximum test item of 500 kilograms, and also a temperature variation from -170 to 150 degrees. The vacuum level is 10 to the -5 torr. So within the facility, what they can do essentially is to test the entire payload, and that is very useful for the system testing, for the and the verification of the systems, all the system on board. So they have the possibility to have a fit-throughs to control and to monitor the functioning of the device, and that is a very useful facility to have. In terms of other capabilities, what they have is a thruster. is a thruster test facility and a vibration test facility, which is essentially is a shaker able to get to 22 kilonewton RMS. They have also an anechoic chamber for electromagnetic interference and compatibility, and that's very important, especially for telecommunication application for telemetry. And the range goes from the 30 megahertz to 80 gigahertz, and that can host again the entire payload in order to test the compatibility of the system. They also have an atmospheric thermal facility, which is able to do also thermal shock using essentially a drop kind of setting. And so you can go essentially from -70 to 170 degrees in a few milliseconds. And that is there are features which are available for monitoring of the performance in of the device. This is, I think, is an Angelo Antoni kind of device in order to do that. Then finally, what they have is a gravity and a weight measurement facility for the payloads, and the moment of inertia, and a clean room for assembling or disassembling of the devices. These are all facilities which are available within practically the same campus in Canberra, and you can understand how useful it is to have all the sort of capability and facility gathered in the same spot for a company, which can save a lot of money in terms of logistics, in terms of accommodation, and so on for the full characterization of the payloads. So moving on, the University of Wollongong, where I come from, this is something which is very close to my heart and is a part of my heritage and contribution to the network. So essentially what we create is a laser facility for single element test. Probably, I'm not sure if everybody is aware of this kind of technique in order to stimulate a single element effect. There are even a commercial system now available for companies to purchase, which are based on a single photon excitation for this kind of test, because it's recognized to be extremely useful for identification of defects during the design and the debugging phase of the project. So this is something which is not able to provide quantitative information on the cross-section versus lateral characterization of the radiation assurance, but is able to give a very interesting and very important feedback on the sensitivity of the device, especially in the design phase. So this is an example. So I'm pretty sure you're familiar with this kind of concept. And this is essentially the idea of the expected outcome from our facility, which is essentially give a weighable fitting of a cross-section calculated in terms of the number of events per number of pulses generated by the system, and plot them as a function of the laser energy used to stimulate that kind of single element effect. So these clearly give us the possibility to have mapping of the sensitivity. Doesn't need to be necessarily single element upset, can be single element latch up, functional interrupt, any type of single element effect in reality, especially if you have the right energy to stimulate those kind of effects. So our essentially is based the whole theory is based on the absorption of light in the substrate of silicon, which is dominated by what we call the linear absorption coefficient, and that is the single photon interaction. So the idea is that one photon is going to generate an electron hole pair. In reality, there are at least another two terms which contribute to that generation rate, which is the non-linear absorption, or the two photon absorption, and what we call the free carrier absorption, which is associated with the fact that we are using semiconductors. And so you can actually have the free carrier wandering around, which you can recombine with your excitation. So the thing there is The thing there is that we are ignoring the free carrier absorption, but we are focusing on these two different processes, the one photon and the two photon absorption, in order to generate enough energy to trigger the single element effect. So in that sense, what we look at is the wavelength, which is able to penetrate enough in silicon and generate a distribution of energy, which is a distribution of events, which is large enough to create enough charge, or a critical charge, which is able to generate and trigger the single element effect. In our case, what we are looking at the range is the range between 800 and 1,200 nanometers in terms of wavelength, where the 1,200 is mainly dedicated to the two photon absorption as above band gap in silicon. So the main parameter that we're considering for our facility is wavelength, is waste dimension, timing of the pulse, and the energy and the peak energy of the pulses. These are the main parameters, and they are the one which essentially are dependent on the type of device which needs to be tested. Clearly, if we are testing something which is not in silicon, gallium arsenide, for example, the wavelength needs to be adjusted. So having a functional adjustable laser source is something which is extremely important for this kind of setup. In the first phase of our network in our development, I'm focusing mainly on the single photon at the moment, simply because is readily available for the customer, and the two photon absorption is something which is very critical and requires a very fine tuning, which may actually take a very long time to develop from scratch. So this is essentially the characteristic of the facility that we are building, and I'm going through it quite quickly. We have at the moment we have an 800 to 1100 nanometers tunable laser, titanium sapphire, which can be extended with some module and pumping device into the 1200 range. And then we have essentially all sorts of devices necessary to monitor the intensity online, the intensity of the beam, the shape of the beam, and particularly the position of the beam in respect to the device. Then we have also devices necessary, for example, to measure the reflectance that we have from the device. And this, again, is important to estimate the effective energy deposited in silicon, which are obviously dependent on the layer of metallizations, on the reflector, on the refractive index of the layers of passivation that the chip has. The system, these are very detailed in reality, kind of presentation where I'm going through most of the systems. But what I would like to suggest is that we need to monitor every single parameter of the beam for this kind of technique. And that's what it makes it a little bit harder than what is actually the usual irradiation using ions, because of the detail of variation, the level of variation you can have if the parameter of the beam is not taken into control. For example, like a duration of the pulse, we're talking about femtoseconds, which means that the measuring the pulse itself is challenging because of the duration of the pulse itself. So an autocorrelator is required in order to measure that. And that needs to be done pulse by pulse, because the effectiveness of generating single element effect depends on the timing and the pulse length. So we have is an integrating sphere that is going to be used for reflectance measurements. And these are some of the approaches I'm going to have to measure the waste, the actual waste of the beam itself, in order to estimate the energy density of the beam within the substrate. And then this is alignment system, which is going to be used for the peak and for the pulse itself within the surface of the device. So what is necessary essentially is to have a macroscopic system which is able to show the surface of the device and the localization of the spot, which is going to be lower than 1 micron. So is probably in the order of 1.2 micron is going to be the spot size, and that needs to be aligned and focus on a specific grid across the device, so that a mapping of the sensitivity can be achieved. In terms of two-photon absorption, the complexity of the setup grows exponentially, because the two-photon absorption allows the focalization of the beam not at the surface, but actually in a certain depth into the substrate. And that is extremely useful in terms of generation of the amount of energy deposition in the right spot, in a sort of modulating essentially the depth of interaction that the laser has with the device under test. What is the problem with that is that changing the intensity of the beam changes, for example, the shape of this distribution of the energy. And so the parameters which are required to have an accurate mapping of the sensitivity, not only in 2D across the surface, but also in 3D, in different layers of the device. I'm thinking, for example, to technology like FinFET, where the position of energy may actually be completely different types of cross-section of the single event effects if they are done in different depth in the substrate. This technique is crucial and must be developed. This is also the reason why we didn't go and buy directly a device from a company in order to provide this kind of service, because we would like to develop this kind of expertise and also have the possibility to be flexible for our customer based on the demands which are coming from them. So these are some of the references to, if you are interested, in terms of the theory which is behind and the performance that this kind of system has been achieved. Particularly, these are from the group of Buchner, which is in US, and Vanderbilt, and from Poget, which used to be part of the same group, and now probably is actually in CNES. It's working in CNES. So I hope this is of interest for what concern the laser facility. Now there is something which is new instead in this network, which probably is kind of unusual. Has been tried in the past in US, but is a kind of unusual for the space industry, which is trying to use X-rays, focused X-rays, high intensity light in order to create a single event effect. And this is essentially comes from the Australian synchrotron, which is located in Melbourne. We have the fortune to have a facility able to generate 3 GeV on in a relatively small facility where there are 8 and 9 beam lines. There are now developing more beam lines for imaging. Particularly what we are collaborating with the NSQN is the medical beam line, where they essentially have the imaging and medical beam line, IMBL, where practically they are accessing synchrotron light emitted by the storage ring into a very long, they have 3 different arches. They have the one which is right close to the storage ring, where the wiggler is and where the spectrum is generated. And then they have the facility, the imaging facility, which is down to a tunnel of 150 meters in order to create the proper magnification factor in respect to the source. And here is where the imaging of the device are performed. The intensity of this facility is obviously very, very high as a synchrotron. In the range of energy which is available is anything between essentially 0 to 300 kilo electron volt. And we call this distribution the pink beam, because in reality we are also able to perform to use a monochromator, which is able essentially to select very narrow range of X-rays from this spectrum. And that clearly depends on where they are sitting. We have a different flux. The typical dose rate for these objects is anything which is between 2 and 12 kilogray per second, which is enormous, and is generated 25 kilowatt of X-ray powers. This is a kind of important because of the capability of this beamline, particularly to essentially create what we call microbeams. And this is, I think, is what very interesting in this facility. The medical beamline is essentially creating now, is developing now a new type of radiotherapy, which is called microbeam radiation therapy. And this therapy is requires a very strong spatial fractionation in order to achieve their radiobiology effectiveness. So it's using a low energy X-rays, but the intensity is such that the penetration is still very, very large. And the necrosis is developed only along the microbeams, which are only 50 micron wide. Instead, the valley, which is essentially where the microbeams are occluded by the microslit collimator, they are very, very low. And for very low, I mean it's lower than the usual radiotherapy treatment, which is a 2 gray. Now we have a kilogray in the microbeam, and we have a few gray in the valley. Now this spatial fractionation generates essentially a radiobiological effectiveness, which is larger than what is expected for light, for photon interaction. We would like to use this technique in order to create essentially a single microbeam, which is able to stimulate the electronics in a very limited, very special focus beam, and then use the temporal structure, the microsecond temporal structure of the synchrotron itself, in order to generate a narrow temporal distribution of the pulses, so that we can use the nanosecond structure of the pulses to count how many pulses of X-ray light they are delivered to the device. So the idea is to use their existing alignment and imaging facility in order to control the positioning of the device, in order to scan the device. And you see that we are able to, at the moment, the team is able to essentially visualize very high detail any type of chip with any kind of magnification, thanks essentially to the imaging beamline. And that is aligned directly instead with the microbeams, and the microbeams can scan across the surface, identifying essentially specific point or specific function of that chip in terms of single element effect. The structure, the microstructure of the synchrotron, as this is a screenshot that I got, a picture that I got from the control room a couple of weeks ago when I was there to do experiments. And you see this peak is a few nanoseconds in width, and the intensity of this peak, the amount of dose delivered in this peak, is something in the order of kilogray. Okay, so we're talking about 10 to the 6 gray per second in terms of capability to deliver dose with this kind of modality. And that's, in my opinion, is very interesting to understand if this technique and if this equipment can be useful to test devices which cannot be decapsulated, and so they cannot be tested using heavy ions or laser. Okay, so this is something which is representing, in my opinion, a very interesting alternative to that technique. Yeah, this is just to highlight essentially the microstructure of the beam. So moving on, the more standard kind of ANSTO provides also another facility, which is Guthrie, which is a cobalt-60 gamma irradiation. So the cobalt-60 rods, they are stored into a water-filled pool, and they can be practically extracted from the pool, and they can irradiate an area uniformly, an area of 1 by 1 meter. So that is a perfect thing, for example, for testing devices which are already on board, or to actually have a total ionizing dose system testing, which hopefully, which is often is not so easy to find because of the size of the source required. The dosimetry, which is the dose rate which is achievable with this cobalt-60 source, is obviously the 2 lines from the cobalt-60, but the dose rate is anything between 0 to 15 gray per minute, which is large enough essentially to comply with the standards defined by ESA. And that is the area which is approximately covered by the field of view of the source. There is also another facility in ANSTO for X-ray irradiation, which is low energy, low dose rate irradiation, which is very useful for within the standard for low dose rate irradiation, published in MIL standards, and that is able to deliver the up to 10 gray per minute over 20 by 20 centimeter square, but it can be fine-tuned using the current, because it's simply a very high current X-ray tube. The dosimetry provided in this facility is obviously very accurate, because the facility complies with the standards ISO, and the Australian standard for irradiation of materials. And so they provide to the customer a free service of dosimetry and a characterization of a distribution of the dosimetry across the sample, if the sample is way too larger than the field of view of the facility. So I'm essentially going to conclude my talk with a table which I extracted from a publication from Puget and from Stephen Buchner, where they suggest essentially how different type of single event effect and characterization can be performed using heavy ion, or for example laser facility, single photon or 2 photons. What I would like to propose within the NSQN initiative is that we can actually add another couple of columns to this plot, where we propose the possibility to use microbeam X-rays as an alternative to laser or to ion for a single event effect, but also the fact that we have now the possibility using the CAS facility to have a microbeam ions, where we can focus on 1 micron or sub-micron resolution our beam, and we can investigate a specific function in a chip using the ions themselves, making in a way a very nice tool for any type of development and characterization. I think this is the end of my presentation, which I hope is not too long in respect to the time which we planned. I would like to thank you very much for this opportunity and the attention. Thank you very much.
Great, thanks a lot, Marco, for the excellent talk and the comprehensive overview. It's really impressive to see the vast amount of facilities and all the very versatile capabilities. So this is really very interesting to see. So I propose we will soon pass to the question and discussion. I think we can still have a few minutes for that. I will just ask you, Marco, to stop sharing. I will just put up one quick slide before we close the recording, just to remind us, as some people connected a bit later, again, that this is part of a series of webinars, so that this is actually the second one. and that also more generally RADNEXT provides essentially an enhancement to the accessibility to irradiation facilities across Europe, plus Triumph, with the next call for beam time opening in June. So of course I invite everybody to follow the website, the LinkedIn feed, and so on. And maybe to transition a bit to what we will have as the next talk, I wanted to say that as we know, high energy protons are quite important for SE testing, and if we look here at the left, it's not so easy. The two main figures of merit are the energy and the flux. It's not easy to find high energy, and by high energy we typically mean 200 MeV protons. This is a summary of the RADNEXT facilities that can provide this, essentially PSI, KVI, now called ParTrek, and Triumph. And in the US, there's a similar situation. Actually, it's mostly medical facilities that are providing this type of beam currently, and of course, other more specialized facilities like Triumph again. But it's quite rare, and this is a very sweet spot for radiation effects testing. So essentially, our next contribution, which will take place on the 18th of May, will be from the TIFPA facility in Trento, so mainly for medical applications, but also for other research, including radiation effects on electronics. So it would be our pleasure to welcome Enrico Verroy from the Trento Institute for Fundamental Physics and Applications in roughly 1 month and a bit more. So this is just to make the introduction, as we usually do, of the next series, and of course invite you to register also for this next edition. So having said this, thanks again, Marco. We will pass to the discussion, and I think we can stop the recording here. I will also stop my share.